everyone. Let's continue our discussion of permutation groups, and in particular cycles. We introduced this cycle notation last time, and it went something like this. So if sigma in S sub n is a cycle of length, let's say k, with non-trivial orbit. And when I say non-trivial orbit, meaning that it has more than one element in the orbit. So if it's cycle of length k with non-trivial orbit, we write sigma equal to sigma of I, comma, start with I. I, comma, sigma of I, sigma squared of I, dot, 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 all the way to sigma to the k minus 1 of I. And what that means then is that sigma, when applied to I, gives us sigma to I. Then sigma applied to sigma of I gives us sigma squared of I, and so on. And then this notation also means sigma raised to the k gives us of I gives us I. A definition here. So cycles. Let's write them as sigma equal to S1, S2 up through S sub k, and tau, let's say that one is T1 T2 up through T, not tau, T1 T2 up through T sub m are disjoint if when we take the corresponding set, so this would be S1 up through S sub k, intersect T1 up through T sub m. All right, if you get the empty set, meaning if these sets are disjoint, then we say that the cycles are disjoint. And so the way that you're going to be able to tell this, if none of the numbers here appear here and vice versa, then you've got disjoint cycles. Now, so for example, 1, 3, 5, and 2, 4. Those are disjoint cycles. All right, so these, cycle notation. These are disjoint. And then cycles, let's say, 1, 3, 5, and 1, 2, 4. These are not disjoint. Now, so let's say like this. So suppose that we have a couple of disjoint cycles. So let's call them sigma and tau. So suppose sigma and tau in S sub n are disjoint. And what I'd like to look at, let's write them out. So let's write sigma equal to S1 through Sk, just like we had before. So S1 up through S sub k, and tau is going to be T1 up through T sub m. Then, actually, I think I'll write it over here. I want to get the formula. We'll say then, for I, some number between 1 and n, what I want to look at is sigma tau of I. And what's this going to look like? Well, there's various choices depending on who I is. Probably gonna be bigger than that. So let's see. It's possible that I is not one of these and it's not one of these. In that case, it's just going to be I. So this would be if I is not in S1 SK union T1 up through T sub M. All right, so if you don't see I appear in either one of these, then sigma is not going to do anything to it, tau's not going to do anything to it, so nothing happens. Let's see, if if I is one of these numbers, then we know that I does not appear in this list right here. So if I happens to be one of the S's, then what we'll get is that it will be S sub, let's say, J plus 1. If I is equal to S sub J, let me make sure I get this right. I is equal to S sub J, where J, the only issue is if J is equal to S sub K. So let's say if J is strictly less than K. And then if it happened that I was equal to S sub K, then we would get S sub 1. So it'd be S sub 1 if I is equal to S sub K. Right. Okay, so what other choice is there? It could be that I is one of these. So if I is, so let's say it like this, it'll be T sub J plus 1 if I is equal to T sub J, where J is less than M. And it's equal to, in the case that I is equal to T sub M, then the output when you run it through tau, it would be T1. So this would be if I is equal to T sub, sorry, this should say J strictly less than M, and then this one should be if I is equal to T sub M. So that's the complete formula, all possibilities of choices of I. If you run it, first apply tau, then apply sigma, this is what you're going to get. And what you want to notice is if you reverse the order, because these are disjoint, you're going to get exactly the same thing. So this is equal to tau sigma of I. And so what's our conclusion? Disjoint cycles commute. So conclusion, disjoint cycles commute. So what that means, or in general, if you think about composition of functions, in general, composition is not a commutative operation. In the symmetric group, if you choose a sigma and a tau at random and you compute sigma of tau and then tau of sigma, you're going to get two different answers. But in the case that you have cycles that are disjoint, then it turns out that they commute. Now here's our first result of this chapter. So this is theorem 9.1. So let's choose some element of S sub n. So let's let sigma be an S sub n. Then, how does this go? Then there exist disjoint cycles. Let's call them mu1 up through mu sub k. such that sigma is equal to mu1, mu2, dot, 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 mu sub k. So what is that saying? That's saying then that every permutation, every element of S sub n can be expressed as a product of disjoint cycles. That's nice. That gives us a way now to use cycle notation to describe every single permutation in S sub n. How do you do it? Take a permutation of S sub n, and we will be able to express it as a product of cycles, which means we never have to use this matrix notation again. Everything can be determined or described in terms of products of cycles. So let's see how the proof goes. And the proof is fairly straightforward. So here's the idea, and I'm going to call them B1 through BK. Okay, so let's let B1, B2 up through B sub K be the orbits. Let's be the orbits of sigma. And now we're going to define the cycle mu sub I by mu sub I of x is equal to, and who do I want it to be? I want it to be sigma of x. If x is an element of B sub I, and it's equal to x, so nothing happens to it if x is not in B sub I. Now, we can say then, the mu sub i's, these are definitely disjoint, right? I mean, the orbits themselves, because it forms a partition of the set of numbers 1 through n, definitely disjoint. So these cycles then, because they are based on the orbits, are definitely disjoint. So then the mi's are pairwise disjoint. And, yeah, let's say, I just want to say because it's a partition, because B1 up through BK is a partition of the set of numbers 1 up through n. And that completes the proof. All right, that's it. We just defined it and identified exactly who these mu sub i's are. So what I want to do now is see how this works in action, right? How this proof, or, the proof tells us exactly how to do it. So let's actually do an example. So let's go in S10. In S10, let's let sigma be, and I'm going to use matrix notation here at first, so we're going to go 1 through 10 at the top. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I'm going to have 3, 5, 7, 3, 5, 7, 4, 2, 9, 1, 10, 8, 6. 1, 10, 8, 6. All right, so now what I want to do is identify the orbits. All right, that's how the proof says. Identify the orbits and then create the cycles based on the orbits. So the first orbit, let's see, so it's going to go 1 goes to 3, which goes to 7, which goes back to 1. 2 goes to 5, which goes back to 2. 3, 4 is its own orbit. 5, 2, okay, then we're going to have 6 goes to 9, which goes to 8, which goes to 10, which goes back to 6. And let's make sure we have everybody here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I've written the orbits down. And if we just follow the order that I've written these down, this tells us exactly who the cycles are going to be. So, sigma is now equal to 1, 3, 7 times 2, 5 times. I don't need to write down 4. By not having 4 show up, by default that means that nothing happens to 4. And so then we'll have a 6, 9, 8, 10. That's it. Identify the orbits, write what happens in order, and then put it in cycle notation. That's it. One way to paraphrase theorem 9.1. So, theorem 9.1 says, what does it say? Well, let's see. Theorem 9.1 says that every permutation, every element of S sub n can be expressed as a product of disjoint cycles, in particular, cycles. And so it says that S sub n is generated by its set of cycles, right? So the set of cycles generates all of Sn, constitutes a generating set. Let's do another example. So let's consider sigma equal to 3, 5, 4, 6, 7, 8, 9. 6, 7, 8, 9. So here's a cycle, and then one more tau, and that's going to be 3, 8, 7. 6, 5, 4. So I guess this is happening in, I don't know, S sub 9 if you like, S sub 10. Any S sub n where n is greater than or equal to 9 will work. Okay? So here we have a couple of cycles. These cycles are definitely not disjoint. What I'd like to do now is express sigma tau as a product of disjoint cycles, right? Sigma tau is an element of S sub 9, let's say, which means, according to theorem 9.1, that there exists some collection of disjoint cycles for which sigma tau is equal to the product of those disjoint cycles. So how do we do this? Well, we do exactly what we did before. We need to find the orbits. So I'm going to write this out. Sigma tau is equal to 3, 5, 4, 6, 7, 8, 9 times 3, 8, 7, 3, 8, 7, 6, 5, 4. Okay, so now I need to identify who the orbits are. So let's see, the orbit of 1, just 1, right? Because as you feed 1 through here, 1 happens, nothing happens, nothing happens. The orbit of 2 is just 2 because we don't see 2 appearing at all here. Now how about 3? So the orbit for 3, as I go through, 3 goes to 8, which goes to 9. So 3 goes to 9. And in fact, you know what? I might as well just be writing these as cycles. In fact, let's be a little bit cleaner here. So as I read right to left, 3 goes to 8, which goes to 9. So 3 goes to 9. Okay, so now what happens to 9? 9, nothing, and then 9 goes back to 3. So 3 times 9. Who's next? So we got 3, 4. How about 4? 4 goes to 3, which goes to 5. So 4 goes to 5. 5 goes to 4, which goes to 6. 6 goes to 5, which goes back to 4. So it closes itself up. So I've done 1, 2, 3, 4, 5, 6. So we'll go 7. So 7 goes to 6. 6 goes back to 7. Oh, nope. Something's wrong here. 7 goes to 6. Oh, right. Which means that 7 goes to 7, so I don't need to list it. 8 goes to 7, which goes back, 8 goes to 7, which goes back to 8. So 8 also stays put. And do I have everybody? Yep, because then I got 9. 9 goes to 3. Right? So here is sigma tau expressed as a product of cycles that's not disjoint, and then it can be re-expressed as a product of disjoint cycles in this way right there. And why does my answer... Oh, because I did it in the opposite order. Okay. So let's try this again now. So let's repeat. For tau sigma, so tau sigma, I'm going to write these in the opposite order now. 3, 8, 7, 6, 5, 4 times 3, 5, 4, 6, 7, 8, 9. 6, 7, 8, 9. All right, so I'm going to start with the lowest number that I see on this list. I see a 3. 3 goes to 5, which goes to 4. So that means that 3 goes to 4. 4, I'm going to start over now. Where does 4 go? 4 goes to 6, which goes to 5. So 4 goes to 5. 5 goes to 4, which goes back to 3, so that closes it up. 3 goes to 4, which goes to 5, which goes to 3. Okay, so I've got 3, 4, 5. Now let's do 6. 6 goes to 7, which goes back to 6. So nothing happens to 6. 7 goes to 8, which goes back to 7. 8 goes to 9. So 8 goes to 9. 9 goes to 3, which goes back to 8. So 9 goes to 8. All right, so there it is. Right, so you want to get your familiar, do some practice problems with this, expressing anytime if you have any permutation by doing this little operation, just figuring out who goes where. You can always express your your permutation as a product of disjoint cycles. Another definition. A cycle of length 2 is a transposition. All right, so transposition is something like there, right there, 3, 9, that's a transposition. When it just has 2 numbers in the parentheses, it's a transposition. 8, 9, that's a transposition. 3, 4, 5 is not. That's a cycle of length 3. It's not a transposition. Here's, let me just make this observation. Let's just look at 1, 2, 3. Definitely not a transposition. This is a length 3 cycle. But what we're going to notice is that this is equal to, well, let me just write this down and let's just check to see if this is true. So on the left-hand side, what is this saying? It says that 1 gets sent to 2, 2 gets sent to 3, and 3 gets sent to 1. So let's see what happens on the right-hand side. 1 gets sent to 2. Good. 2 gets sent to 1, which gets sent to 3, so 2 goes to 3. And then 3 gets sent to 1, right? So this equality is true. Let me try it again. Let's do this one. 1, 3, 5, and 7. And I'm going to write it down, so this is going to be 1, 7, 1, 5, 1, 3. Let's make sure that this is true. So let's see, I'm going to feed a 1 through here. 1 goes to 3. That's a match. Now let's feed a 3 through. 3 goes to 1, which goes to 5. All right, so 3 goes to 5. Good. 5. 5 goes to 1, which goes to 7. So 5 goes to 7. That's a match. And then the last one, 7 goes to 1. Right? So what's the trick here? What did I do? I wrote down transpositions like this. Every one of them starts with my first number, right? In both of these cases, I put a 1 in the beginning of each one of those. And then I worked my way backwards, 1, 7, 1, 5, 1, 3. In this first example, 1, 3, and then 1, 2. And so this is a little trick that allows us to write any cycle as a product of transpositions. Yeah, so this little trick right here works in all cases. And this is not the only way to do it, but here's one way to do it. So let's say more generally. So the formula goes like this. We would have, now let's write it like this, A1, A2, up through A sub k, where these are just numbers between 1 and n, is equal to, so how did this go? A1 comma AK. A1 comma AK minus 1. And you work your way backwards. Eventually you'll get to A1 comma A2. Guaranteed, this one on the right is equal to the one on the left. So this gives us a way to express every cycle as a product of transpositions. And so this is really a corollary of the previous theorem. So let's call this corollary 9.2, and this is going to be very useful. Every permutation in S sub n, here obviously n greater than or equal to 2, can be expressed as a product of transpositions. How does the proof of that go? Well, let's see. We know that every permutation can be expressed as a product of cycles, and every cycle can be written as a product of transpositions. End of story. So proof would go like this. Let's let sigma be an element of S sub n. Then sigma is equal to mu1 up through mu k, some product of disjoint cycles, right? So where, or let's say for some collection of disjoint cycles, mu1 up through mu k. So step 1, express sigma as a product of cycles. The disjointness is not really necessary, but it's true that we can do it with disjoint. So now, express each mu sub I as a product of transpositions using this trick that I just did. So we'll say using the trick. I mean, it's not really a trick, so I put that in quotes. The trick above. That's it. And so let's see, what's a way to think of this? Here's another way to say this corollary. We can restate. Let's go like this. So let's let T sub n, which is be the subset of S sub n, so let's see, be the collection of all transpositions of S sub n. So it's not a subgroup, it's just a collection of transpositions. T sub n is the set of all possible transpositions that you can form from the numbers 1 through n. So now we can restate corollary 9.2 as Sn is equal to the subgroup generated by the set of transpositions. So the set of transpositions generates S sub n. So this means that we've got two different ways to express any permutation. So we now have two ways to represent any element of S sub n, and each one can be useful depending on the situation. So the first one, right, as a product of disjoint cycles, and then the second one as a product of transpositions. Right? So each one of these can be useful depending on the setting. One thing that's true up to order, so the disjoint cycle notation or representation, the disjoint cycle representation is essentially unique. So representation is unique up to order. So what that means is there's essentially one way, if you want to express your permutation as a product of disjoint cycles, there's essentially one way to do it. All right? You can reorder them because disjoint cycles commute, but other than that, that's all you get. But it's not unique when we do transposition, so maybe we should end with this. Yeah, actually, this is a good place to stop right after this. So, a decomposition into a product of transpositions is not unique, right? So you can express any permutation as a product of transpositions, but there are many factors, an infinite number of ways to do this. But here's just one example. So we've got 1, 2, 3. Remember, the trick to do this would be 1, 3, 1, 2. But now 1, 2, 3 is equal to the cycle 3, 1, 2. All right, I just moved the 3 to the front there. And this, if I use that same trick, is going to be 3, 2, and then 3, 1. Right? Definitely not the same, right? So disjoint cycle, transposition decomposition is non-unique. Okay, in fact, let me just do one more while I'm here. This will be a good place to leave off, actually. So notice this. In fact, let's do it this way. Example, the identity transposition is equal to the product 1, 2 times 1, 2, which is equal to the product 1, 2, and then 2, 3, 2, 3, 1, 2. So in fact, notice I just expanded. This is the identity, so is 2, 3 times 2, 3, so I just inserted the identity. You can keep expanding this and expanding and expanding, so there's actually an infinite number of different ways to represent any permutation as a product of transpositions. Okay, so we'll stop here and pick up with that next time.